Put the safety doors on manual override.
John, I cannot do that! Hopper, get out!
In my group, we study and develop materials to make nuclear power safer. If you want to do a neat demo, we can actually make some stainless steel from scratch and fire up the arc melter.
Yes, I definitely want to do that.
Okay. So we have a few projects in this lab. One of them is to produce what I call the fuel cladding of the future. An element that we use to make fuel cladding, which protects the fuel from the water and keeps it all together. At Fukushima, the simultaneous earthquake and tsunami knocked out the reactor and its backup safety systems, so the reactor wasn't able to keep the core cool. The fuel got so hot that it boiled the surrounding water into steam, which reacted with the zirconium in the fuel rods. Unfortunately, when zirconium reacts with steam, it also makes hydrogen gas, and it's the hydrogen gas that exploded. We're developing new combinations of zirconium and stainless steel that don't react with steam to make hydrogen. So this right here is a zirconium steam oxidation facility. We take different alloys of zirconium, cut into little pieces, then put them through hanging on a bunch of strings in this chamber right here, and then send in steam at 400 degrees Celsius to simulate what would happen in a nuclear reactor in an accident condition. There's a second project in which we can measure material property changes as they happen during radiation, using a technique that's kind of a mouthful. We call it dual heterodyne transient grating spectroscopy. These are critical properties for materials to survive in nuclear reactors. These experiments have typically taken months to years for people to do, and now for the first time, we can explore material properties like stiffness and how well heat flows through materials using this benchtop experiment, and take an experiment that used to take years and do it in hours. That's going to help us design new materials to make safer reactors. Our lab's coming up with the first way that we know about, where we can actually measure the stored energy, tiny amounts of energy. We're talking microjoules that usually you can't even see. We can take tiny pieces of these materials, smaller than a grain of sand, and using a nanocalorimeter, or an energy measurement device on a chip, we can tell how much energy radiation has left behind, and therefore measure the amount of damage to the material. So the big contraption you see before you is our home-built and home-building vacuum atomic force microscope. We don't want anything to stick to anything in a reactor, because then you might get this, the technical term for what you get is CRUD, believe it or not. Stands for Chalk River Unidentified Deposits. All it is it's corrosion products that stick to the fuel rods and get super radioactive. It's one of the big problems in reactors today, and we think we have a way to solve it. The atomic force microscope actually brings a little piece of this crud in contact with a material and measures how hard it is to pull it off. And that's the stickiness that we're measuring. But we have to test it out in the lab in this sort of contraption to know if we're right.